tiny arrows have to line up. When they do, an answer appears, but nudge one of them just slightly and the answer can disappear. So the real question is not why quantum computers are powerful, it is why they are so easy to break. You have probably heard the usual explanation. A normal bit is 0 or 1. A qubit is often described as 0 and 1 at the same time, but it is not the useful explanation, because when you measure a qubit, you still get one result, 0 or 1, not both. So the important part is not what you see after measurement, it is what was there before. For this video, think of an amplitude as an arrow. The length matters, but the direction matters too. That direction is called phase. And because amplitudes behave like arrows, they can do something probabilities cannot. They can cancel. That is where interference begins. Point two amplitudes the same way, and they build. Point them against each other, and they cancel. Quantum computer is not simply trying every answer at once. The point is more precise. Arrange the amplitudes so the wrong paths cancel, and the useful paths reinforce. The answer appears because the interference pattern was controlled. Interference only works while those directions survive. If one phase drifts, the result changes. If many phase drift, the pattern is lost. That survival is called coherence. Classical information can often survive small shaking, but quantum information depends on a tiny angle. It does not live only in 0 or 1, it lives in phase. So, what destroys phase? The environment. A qubit is not just a symbol, it is a physical object inside a physical machine. There is heat, there are electromagnetic fields, there are vibrations, there are defects in material. Each one can interact with the qubit. Maybe only a little, but a little can be enough. The environment does not need to completely destroy the qubit, it only needs to pick up a trace of information. If the environment becomes slightly different depending on the qubit state, information has leaked out. And once that happens, the clean phase relationship is no longer available to the qubit itself. That is decoherence. Now the problem becomes computational. A quantum circuit is a choreography of amplitudes. Each gate rotates them. At the end, the wrong paths should cancel, and the useful ones should build up. But if decoherence shifts the phases, the choreography breaks. The answer no longer stands out. The computation turns into noise. So the hard part is not just making qubits. It is keeping them coherent long enough to calculate. This is why quantum computers look so strange. They are not cooled to nearly absolute zero because it looks futuristic. They are cooled because heat is motion. Motion means interaction, and interaction causes decoherence. So a quantum computer is not just a calculator. It is an isolation machine. A machine built to keep a tiny quantum system quiet, while the rest of the universe tries to disturb it. But even that is not enough. No physical qubit is perfect. So quantum computers need error correction. For classical information, this is easy to imagine. If one bit is fragile, copy it. If one copy flips, the majority still tells you the original value. But quantum information cannot be copied like that. So quantum error correction has to be more subtle. It spreads one logical qubit across many physical qubits. Then it checks for signs of errors without reading the quantum state itself. That is why more qubits alone is not the real goal. Physical qubits are not the same as logical qubits. The real goal is protected quantum information. So yes, qubits can be in superpositions, but that was never the full story. The real story is interference. Interference needs phase. Phase needs coherence. And coherence is what the environment keeps destroying. A quantum computer is not powerful because it escapes physics. It is powerful because it uses physics with extreme precision. But the rest of the universe is also physics. So building a quantum computer means keeping quantum information alive. Just long enough to be useful. A machine that tries to keep reality quiet.